Hi, I know that calculus can feel like a mountain of disconnected rules. You learn the power rule one day, the chain rule the next, and by the time you get to implicit differentiation or partial derivatives, it's easy to feel lost. That's why I've put together this complete compilation. I'm going to start at the very beginning with the concept of a limit and the definition of a derivative. From there, I'll move through every major rule: power, product, quotient, and chain, and then apply them to real-world problems like finding tangent lines and optimization. I'll even step into multivariable calculus with an introduction to partial derivatives. This is designed to be your go-to resource. Use the timestamps in the description to jump to the specific rule you're struggling with, or watch the whole thing through to see how these concepts actually connect. Let's get started. When we looked at finding the gradient or slope of a linear function f of x in an earlier video, we took 2 points on the line and calculated the rise divided by the run, or the change in y with respect to x. This gave us the gradient or slope of the function. So looking at our function y is equal to fx on the left hand side of the board, I've marked in 2 points on the x-axis. So I've marked in x, and then I've marked in x plus h, so h is some distance from x. The equivalent points on the y-axis are f of x and f of x plus h. So in this case, the change in y with respect to the change in x is equal to, so the change in y is f of x plus h minus f of x divided by the change in x. So that's x plus h minus x. Let's take this a stage further. Let's look at this non-linear function here. How do we find the slope of this? Well, there's not one single slope, but many. What we can do is find the slope of the tangent at any point on the curve. That's where derivatives come in. The derivative of a function gives us another function, which is the gradient of the tangent to any point on the curve. I've plotted the nonlinear function f of x on the left of the board and marked 2 points on the x-axis, x and x plus h. We saw with a linear function we could take 2 points on the line and calculate the gradient of the slope, which would be a constant. Let's go with this approach now and draw a secant line from point x on the x-axis to x plus h in an attempt to calculate the gradient of the tangent to the curve at point x. As you can see, the secant line is an approximation of the tangent we want to calculate, but not a very good one. Now let's make h smaller so that the point x plus h on the x-axis moves closer to the point x on the x-axis. This therefore moves the value of h closer to 0. Remember, h is 0 at point x on the x-axis. Now if we draw another secant line, so that's the green line on the diagram, we see that this is still an approximation to the gradient of the tangent at point x on the x-axis, but it's a better approximation than the first. So it's a better approximation than the blue line that we first drew. So extending this, we find that the closer h gets to 0, the better the approximation. When h is 0, we are at point x on the x-axis, and we have the tangent to the curve. So we can say that the tangent to the curve at point x is the limit as h approaches 0 of f of x plus h minus f of x divided by x plus h minus x, which is the limit as h tends to 0 of f of x plus h minus f of x divided by h. So now we can use this to find the derivative of a function. The derivative of a function will be another function which will give us the gradient of the tangent at any point on the graph of that function. So let's use this to find the derivative of the function f of x equals x squared plus 3. So the limit as h tends to 0, if we now substitute x plus h into the function, we get x plus h all squared plus 3, and then subtract x squared plus 3 from it, and divide all that by h. So expanding that out, we get the limit as h tends to 0 of x squared plus 2xh plus x plus h squared plus 3 minus x squared plus 3 divided by h. Simplifying this further, this becomes the limit as h tends to 0 of h multiplied into 2x plus h, all divided by h, which is the limit as h tends to 0 of 2x plus h. So as h tends to 0 in this limit, it tends to 2x. So 2x is the derivative of the function x squared plus 3. So f prime x is equal to 2x. And that will give us the gradient of the slope for any value of x. The power rule simplifies the way we take derivatives of polynomials. In the video I made on limits and derivatives, we looked at the derivative of a function f of x, or f prime, being the limit as h tends to 0 of f of x plus h minus f of x, all divided by h. This allowed us to find the gradient of a tangent to a function f of x. The good news is there is an easier way of finding derivatives. This is called the power rule, and the power rule simplifies the way we take derivatives of polynomials. So let's say we have a function f of x and it's equal to x to the power n, where n is not equal to 0. The derivative of f of x, or f prime x, is then equal to n multiplied by x to the power of n minus 1. So let's see how this can be applied to a real polynomial. So we have a function f of x is equal to x to the power of 6 plus 2x squared minus x cubed plus 2x plus 3. We can apply the power rule to each of the terms individually to get the complete derivative. Let's take x to the power of 6 first. For this term, n is equal to 6. So according to the power rule, we multiply x by 6 and decrement the power by 1. So we get 6 times x to the power of 6 minus 1, which is equal to 6x to the power of 5. So let's now start building up the derivative of f of x, or f prime x. So the first term we can put in is 6x to the power of 5. Now let's look at the second term, 2x squared. N in this case is 2, so we multiply the x term by 2. It's already multiplied by 2, so that becomes 2 times 2 multiplied by x, and we decrement the power by 1. So it's x to the power of 2 minus 1. This equals 4, because we have 2 times 2, multiplied by x to the power of 1, which is just 4x. We can now add this second term, so plus 4x, to the derivative of f of x, f prime x. So currently we have f prime x is equal to 6x to the power of 5 plus 4x. Now let's take the third term, minus x cubed, where n is 3 in this case. Let's think of this term as having a coefficient of minus 1. So applying the power rule, we multiply this coefficient by n, which in this case is 3. We then multiply that by x to the power of n minus 1. So n minus 1 in this case is 3 minus 1. So that gives us minus 3x squared. So we can now add this third term to the derivative of f of x, or f prime x. So once we've added this, f prime x is now 6 times x to the power of 5 plus 4x minus 3x squared. Now let's look at the term 2x in our function f of x. Now in this term, although you can't see a power of x, x is actually to the power of 1, so n is equal to 1. So this time we multiply the coefficient of x, which is 2, by n, which is 1, and then we multiply that by x to the power of 1 minus 1. So 2 times 1 gives us 2, and x to the power of 1 minus 1 gives us x to the power of 0. Now anything to the power of 0 is 1, so we're left with the value of 2. So let's add this latest term to the derivative of f of x. So now we have the derivative of f of x, or f prime, is equal to 6x to the power of 5 plus 4x minus 3x squared plus 2. So now let's take a look at our final term, which is 3. Now 3 is a constant, so it's not multiplied by x. So when we apply the power rule to a constant, the derivative is always 0. So the derivative of 3, the constant with respect to x, is 0. As we have no further terms to add, that completes the derivative of our function f of x. So the complete derivative of f of x, or f prime, is equal to 6 times x to the power of 5 plus 4 times x minus 3x squared plus 2. Now let's see how we can apply the power rule to negative powers. So this time our function is x to the power of minus 2 plus 3 times x to the power of minus 4. So we can apply the power rule in exactly the same way as we did before. So let's take our first term, which is x to the power of minus 2. So in this case, n is minus 2. So if we think of x to the power of minus 2 as having a coefficient of 1, we multiply the coefficient by n. So we get minus 2 times 1 multiplied by x. And this time we decrement the power by minus 1. So the power is minus 2. So if we subtract minus 1 from minus 2, we get a minus 3. So if we put the whole thing together, we get minus 2 times 1, which is minus 2, multiplied by x to the power of minus 3. So if we now start building up our derivative of f of x, so f prime x, so if we add our first term in, we have f prime x is equal to minus 2 multiplied by x to the power of minus 3. So if we now look at our next term, 3x to the power of minus 4, in this case n is equal to minus 4. So if we now apply the power rule, we multiply the coefficient of x, which in this case is 3, by minus 4, which is n, and then multiply that by x, and we decrement the power of x by 1. So the power of x is 4, so we decrement that by 1. So we are left with x to the power of minus 5. So if we put all that together, we have minus 4 times 3, which gives us minus 12, multiplied by x to the power of minus 5. If we now add this term into our derivative, this is our final term. So we now have the derivative of f of x, or f prime x, which is equal to minus 2 times x to the power of minus 3 minus 12 times x to the power of minus 5. So let's now look at another example of using the power rule to differentiate a function. This time, let's look at a function which has got fractional exponents. So our function on f of x is equal to x to the power of a half plus 2 times x to the power of a quarter plus x to the power of minus 1/3. So let's take our first term. We have x to the power of a half. So in this case, n is equal to a half. And if we think of the coefficient of x as being 1, we have n, which is a half, multiplied by 1, multiplied by x, and we need to decrement the power of x by 1. So the power of x is a half, and we need to decrement that by 1, which leaves minus a half. So putting all that together, we have a half times 1, which is a half, multiplied by x to the power of minus a half. So that is the same as x to the power of minus a half divided by 2. So we can add this first term into the derivative of f of x. So we have f prime of x is equal to x to the power of minus half divided by 2. So our next term to differentiate using the power rule is 2 times x to the power of a quarter. So in this case, n is equal to 1/4, and the coefficient of x in this term is 2. So we multiply n, which is a quarter, by the coefficient of x, which is 2, and then we multiply that by x and decrement its power by 1. So its power n is equal to a quarter minus 1. So a quarter minus 1 leaves us minus 3/4. So putting all that together, we have 2 times a quarter, which leaves us with a half, multiplied by x to the power of minus 3/4, which is the same as x to the power of minus 3/4 divided by 2. So if we add this latest term into the derivative of f of x. So f prime x is now x to the power of minus half divided by 2 plus x to the power of minus 3/4 over 2. And last but not least, the final term we have to differentiate is x to the power of minus 1/3. So in this case, n is equal to minus 1/3, and the coefficient of x is 1. So we multiply n by the coefficient of the x term, so we have minus 1/3 times 1, and then we multiply that by x, and we decrement its power by 1. So its power is minus 1/3, so we subtract minus 1 and get minus 4/3. So if we put all that together, we have minus 1/3 times 1, which is minus 1/3, multiplied by x to the power of minus 4/3. So that is equal to minus x to the power of minus 4/3 divided by 3. So adding this last term in, we have the derivative of f of x, or f prime x, which is equal to x to the power of minus half divided by 2, plus x to the power of minus 3/4 divided by 2, minus x to the power of minus 4/3 divided by 3. So we want to find the derivative of y is equal to x cubed plus 3x squared all to the power of 8. Now we could multiply out the brackets, however there's an easier way using the chain rule. First of all, we need to create an inside function. So our inside function effectively substitutes for the function inside the brackets. So let's say u is equal to x cubed plus 3x squared. So that's our inside function. And now we need an outside function. So our outside function is y is equal to, now we take our u and we place it to the power of 8. That's our outside function. We now apply the chain rule, which is dy by dx, which is what we want to find, is equal to dy by du multiplied by du by dx. So dy by du is the derivative of y is equal to u to the power of 8. So to differentiate that, we multiply 8 by u, and the power we decrement by 1. So it's 8u to the power of 7. And the next thing we need to find is du by dx. So we need to differentiate the function x cubed plus 3x squared. So x cubed, when differentiated, is 3x squared plus, and differentiating 3x squared, it's the power of 2 multiplied by 3, so that gives 6x, and then the power decremented by 1, so it's 6x. So now we have dy by dx, which is what we want to find, is equal to dy by du, 8u to the power of 7, multiplied by du by dx. Now that's 3x squared plus 6x. So now we can substitute back in the value for u. So we have 8, and we know u is equal to x cubed plus 3x squared, and that's multiplied by 3x squared plus 6x. So that is our answer. So in our second example, we want to differentiate y is equal to x squared plus 5x minus 6 all to the power 9. So using the chain rule, our inside function, let's call it u, is equal to x squared plus 5x minus 6. And our outside function is y is equal to u to the power of 9. So dy by dx is equal to dy by du multiplied by du by dx. So let's first take dy by du, and that is equal to, so we want to differentiate u to the power of 9, so that is 9u to the power of 8, and du by dx is equal to Now we need to differentiate x squared plus 5x minus 6. So derivative of x squared is 2x plus derivative of 5x is 5 and the derivative of minus 6 is 0. So dy by dx, which is what we want to find, is equal to dy by du, so it's 9u to the power of 8 multiplied by 2x plus 5. Now substituting for u in this expression, we have 9 and then u is equal to x squared plus 5x minus 6. So x squared plus 5x minus 6 multiplied by 2x plus 5. And that's our answer. So we have the function y is equal to x squared and we want to find dy by dx. Now the important thing to note here is while the derivative of a sum is the sum of the derivatives, the derivative of a product is not the product of derivatives, and that's where the product rule comes in. So let's see why that is true. Now we know the derivative of x squared is 2x. So let's suppose that y is equal to x times x. We make the first x u and the second x v. Then if that were true, dy by dx would equal to du by dx multiplied by dv by dx. Now u in this case is x, so the derivative of x would be 1 multiplied by dv by dx. V is equal to x. So the derivative of that would also be equal to 1. So 1 times 1 would equal 1, which is, as we know, incorrect because dy by dx is 2x. So this is where the product rule comes in. Now the product rule says dy by dx is equal to u times dv by dx plus v times du by dx. So let's plug our numbers in. So u is x. Now dv by dx, so v is x, so the derivative of it is 1 plus v is x, and that's multiplied by du by dx. So u is x, so the derivative is 1. That is equal to x plus x, which is equal to 2x. So in our second example, we want to differentiate y is equal to x cubed plus 1 multiplied by the square root of x. So in this case, let u equal x cubed plus 1 and v equal the square root of x, or x to the power of a half. So applying the product rule, we have dy by dx is equal to u multiplied by dv by dx plus v times du by dx. So dy by dx is equal to u, which is x cubed plus 1, and dv by dx. So v is the square root of x, so dv by dx is 1 divided by 2 times the square root of x, and that's plus square root of x times and du by dx. So u is x cubed plus 1, so the derivative of that is 3x squared. So previously, when we've been looking at differentiation, we've always had y as the subject of our equation, so y is equal to some function of x. This is known as explicit differentiation. In the example, x squared plus y squared equals 25. This is no longer the case, and we need to use something called implicit differentiation. We want to differentiate this with respect to x, so we want d dx of x squared plus d dx of y squared is equal to d dx of 25. differentiating the x squared term is fairly straightforward. It's 2x. And also the constant term 25, that becomes 0. But we want to differentiate y squared with respect to x. So how do we do that? We need to apply the chain rule to do this. So applying the chain rule to d dx of y squared gives us the derivative with respect to y of y squared multiplied by dy by dx. So this gives us, so the derivative of y squared with respect to y is just 2y. And then dy by dx, well, we don't know what the function of x is, so we leave it as dy by dx. So we now have 2x plus 2y dy dx is equal to 0. So 2y dy dx is equal to minus 2x, and therefore dy by dx is equal to minus x over y. So to differentiate a function of y with respect to x, we differentiate with respect to y and then multiply by dy by dx. So now let's apply what we learned in example 1 to example 2. So we want to differentiate with respect to x, y squared plus x cubed minus y cubed plus 6 equals 3y. So let's first differentiate y squared. So the derivative of y squared with respect to x is 2y multiplied by dy by dx. The derivative of x cubed with respect to x is 3x squared. And the derivative of minus y cubed with respect to x is minus 3y squared times dy dx. The derivative of 6 with respect to x is 0. And that would equal the derivative at 3y with respect to x, which is 3 times dy by dx. So now let's rearrange our terms so we get all the terms multiplied by dy by dx together. So we have 3x squared equals 3 dy dx plus 3y squared dy dx minus 2y dy dx. So 3x squared is equal to dy dx multiplied by 3 plus 3y squared minus 2y, and dy dx therefore equal to 3x squared divided by 3y squared minus 2y plus 3. So that's our answer. So we'd like to differentiate y is equal to x divided by x plus 1. Now when we have a function in the form of y is equal to u divided by v, where in this case u is equal to x and v is equal to x plus 1, we can apply the quotient rule to differentiate the function. Now the quotient rule would say dy by dx is equal to v du by dx minus u times dv by dx, and that's all divided by v squared. So dy by dx in our case is equal to v, which is x plus 1, multiplied by du by dx, where u is equal to x. So du by dx is equal to 1 minus u, which is x, times dv by dx, where v is equal to x plus 1. So dv by dx is equal to 1. And that's all divided by v squared, which is x plus 1 all squared. So dy by dx is equal to x plus 1 minus x divided by x plus 1 all squared, which is equal to 1 divided by x plus 1 all squared. In our second example, we have y is equal to 1 minus x squared divided by 1 plus x squared. So y is in the form of u divided by v, where u is equal to 1 minus x squared and v is equal to 1 plus x squared. So we can again apply the quotient rule, which is dy by dx equals v times du by dx minus u times dv by dx. And that's all divided by v squared. So in our case, dy by dx is equal to v is equal to 1 plus x squared, du by dx, where u is equal to 1 minus x squared. So du by dx is minus 2x times minus 2x minus u, which is 1 minus x squared, multiplied by dv by dx, where v equals 1 plus x squared. So dv by dx is 2x, and that's all divided by v squared, is 1 plus x squared, all squared. So dy by dx is equal to minus 2x minus 2x cubed minus 2x plus 2x cubed, all divided by 1 plus x squared, all squared, which equals minus 4x divided by 1 plus x squared, all squared. So we want to differentiate the function y is equal to x cubed minus 4 all squared multiplied by 2x plus 5 cubed. So to do this, we need to use a combination of the product and the chain rule. So first of all, let's apply the product rule. So to do that, we can split into two functions. U equals x cubed minus 4 all squared, and v equals 2x plus 5, and that's cubed. So the product rule says dy by dx is equal to u times dv by dx plus v times du by dx. So dy by dx is equal to u, which is x cubed minus 4 all squared multiplied by dv by dx. So to work out dv by dx, we need to apply the chain rule, because we know that v is equal to 2x plus 5 cubed. So we need an inside function. So let's call the inside function g, which is equal to 2x plus 5. And we need an outside function. So v is equal to g cubed. dv by dx will now equal dv by dg multiplied by dg by dx. dv by dg is the derivative of g cubed, which is 3g squared, multiplied by dg by dx. So g is 2x plus 5, derivative of that is 2. So t dv by dx is 6g squared. And if we substitute for g, we get 6. So g is 2x plus 5. And that's all squared. So that's multiplied by 6 times 2x plus 5. That's squared. So plus, so v in this case is 2x plus 5 cubed. 2x plus 5 cubed. And that's multiplied by du by dx. So if we again move over to the right hand side of the board and we say u is equal to x cubed minus 4 all squared. So again we need to apply the chain rule here. So our inside function, let's call it h, is equal to x cubed minus 4, and u is h squared. So applying the chain rule, we have du by dx is equal to du by dh multiplied by dh by dx. Du by dh, so u is h squared, so du by dh is 2h multiplied by dh by dx. So h is equal to x cubed minus 4. So the derivative of that is 3x squared. If we now substitute for h, so h is x cubed minus 4. This is equal to 2x cubed minus 4 times 3x squared, which is 6x squared times x cubed minus 4. If we go over to the left hand side and put that in our equation, so it's multiplied by 6x squared x cubed minus 4. So we can now tidy this up a little bit and say dy by dx is equal to, so we need to factorize this expression. We can take a 6 out and an x cubed minus 4, and we can remove 2x plus 5 squared. And then we can multiply that into a bigger bracket of x cubed minus 4 plus 2x plus 5 multiplied by x squared. And that's our answer. Suppose we want to find the equation of a tangent at a point on a curve. How do we do it? This is best illustrated by example. On the left hand side, I've drawn the graph of y is equal to x squared plus 2. And I've drawn a tangent to the curve at point x equals 1 and y is equal to 3. Given just this information, what is the equation of the straight line formed by the tangent? We know that the equation of a line is given by the formula y equals mx plus constant c, where m is the gradient or slope of the line and c is a constant where the line cuts the y-axis at x equals 0. In an earlier video, I demonstrated how to calculate the gradient of a line using rise divided by run. When using this method for calculating the gradient, we were given 2 points on the line. We could then use these 2 points to calculate the gradient of the line by using the formula m for gradient is coordinate y2 minus y1 divided by coordinate x2 minus coordinate x1. In our example though, we have just one coordinate. In this case, we can use differentiation to find the gradient. So if y is equal to x squared plus 2, the derivative of y with respect to x, dy by dx, is equal to 2x. So now to find the gradient of the line, we plug in the x coordinate that we know. So in this case, the gradient m is equal to 2 multiplied by x. And x in this case is the value of 1. So it's 2 multiplied by 1. The gradient is 2. So now we have the gradient of the line. We can plug this information into our equation y is equal to mx plus c. So y is equal to m, which is the gradient, which we know is 2, multiplied by x plus a constant c. We also know an x and y coordinate of this line as it touches the curve y is equal to x squared plus 2 at the point 1, 3. So x is 1 and y is 3. So if we substitute the values of x equals 1 and y is equal to 3 into this equation, we can determine what the constant value is. So if y is equal to 3, we have 3 equals 2 times 1 plus the constant c. So if we solve this equation, c is equal to 1. So substituting this value of c back into our equation of y is equal to 2x plus c, we have y equals 2x plus 1. And this now gives us the equation of the tangent to the curve of y is equal to x squared plus 2 at the point 1, 3. So now let's take a look at another example. Let's find the equation of the tangent to the curve of y is equal to x cubed plus 2x squared plus 1 at coordinates x equals 1 and y is equal to 4. So firstly, let's find the gradient or slope of the line by differentiating the function with respect to x. So dy by dx is equal to, so the derivative of x cubed is 3x squared plus the derivative of 2x squared is 4x. So therefore we have our gradient m is equal to 3x squared plus 4x. So at coordinate x equals 1, the gradient m is 3 times 1 squared plus 4 times 1, which equals 7. So now if we plug this into the equation of a line, which is y is equal to mx plus c. So in our case, y is equal to the gradient m, 7, multiplied by x plus constant c. So now if we plug our coordinates x equals 1 and y is equal to 4 into this equation and solve for c, we get a value of y, which is equal to 4, is equal to 7 times x, which is equal to 1, plus c. So solving for c, we get c equal to minus 3. So the equation of the tangent to the curve y is equal to x cubed plus 2x squared plus 1 at coordinate x equals 1 and y equals 4 is y equals 7x minus 3. So looking at another example, let's find the equation of the tangent to the curve y is equal to x squared divided by 2 plus 3 at coordinates x equals 2 and y is equal to 5. So first, let's find the gradient of the tangent. We do that by differentiating y is equal to x squared divided by 2 plus 3. So dy by dx is equal to 2x divided by 2. So our gradient m is equal to x. So at coordinate x equals 2, the gradient m is equal to 2. So putting this into the equation of our line, which is y equals mx plus c, we get y is equal to 2x plus c. So our coordinates x is 2 and y is 5. We can use these to solve this equation for our constant c. So if y is equal to 5, 5 equals 2 multiplied by 2 plus constant c. So solving for c, we get c is equal to 1. So now if we put all this together, we have y is equal to 2x plus 1. This gives us the equation of the tangent to the curve y is equal to x squared divided by 2 plus 3 at the coordinates x equals 2 and y equals 5. We have a graph of y is equal to x cubed minus 6x squared plus 9x plus 1. And we want to determine the stationary or maximum minimum points on the curve. From visual inspection, we can see where they are. But how do we find these coordinates mathematically? So we can see that the maximum point is here and the minimum point is here. These are known as stationary points on the curve. At these points, the rate of change of y with respect to x is 0. So at these points, dy by dx is equal to 0. So to determine these stationary points, we need to differentiate our function y is equal to x cubed minus 6x squared plus 9x plus 1. So differentiating our function, we get 3x squared minus 12x plus 9. And if we set that equal to 0 and solve this quadratic equation, we'll be able to find the coordinates of the maximum and minimum points on the curve. So let's solve this equation. So we can divide both sides by 3. So we get x squared minus 4x plus 3 equals 0. And we can factorize it. So x minus 1 multiplied by x minus 3 is equal to 0. So therefore x is equal to 1 and x is equal to 3. So if we now put these values of x equals 1 and x equals 3 into our equation for y is equal to x cubed minus 6x squared plus 9x plus 1, we'll be able to find the coordinates of the stationary or maximum and minimum points on the curve. So let's take x equals 1 and y will equal, so x cubed is 1 minus 6x squared, so x is 1 again, so it's minus 6 plus 9 times x, so x is 1, so 9 times 1 is 9 plus 1. In this case, y is equal to 5. If we put x equals 3 into the equation, we get y is equal to 27 minus 54 plus 27 plus 1. So y is equal to 1. So if we plot these coordinates on the curve, x is equal to 1 and y is equal to 5. So here we have x is equal to 1 and 5. And here we have x is equal to 3 and 1. Y is equal to 1. So it's quite easy to determine where the maximum and minimum points are on the curve when you can actually see the curve. So what happens when you can't see the curve? How do we determine whether those points are either a maximum or a minimum? So to do that, we can take the second derivative. So the second derivative is d2y by dx squared. So effectively, we differentiate the gradient function. The gradient function is dy by dx. We already have dy by dx, and we know it's 3x squared minus 12x plus 9. So d2y by dx squared is the derivative of this gradient function. So in this case, it's 6x minus 12. So now we have that, we can put our values for x equals 1 and x equals 3. So when x is equal to 1, if we plug that into our equation 6x minus 12, we get, so 6 times 1 minus 12 is equal to minus 6. And where x is equal to 3, we have 6 times 3 minus 12, and that gives us plus 6. So what does that tell us about whether the point on the curve is a maximum or minimum point? If it's a negative number, so if d2y by dx squared is less than 0, then it's a maximum. And if d2y by dx squared greater than 0, then it's a minimum. So we can show this on the curve. For the maximum point, as you can see, curve increases up to the stationary point and then decreases. And similarly, when we have a minimum point, the curve decreases to the stationary point and then starts increasing. So by finding the rate of change of the gradient function, we can determine the maximum and minimum. So when the gradient starts to decrease, it becomes less than 0, it's a maximum point. And when the gradient or the rate of change of the gradient starts to increase, we know it's a minimum point. If we look at the limit as x tends towards 4 of the expression x squared minus 16 divided by x minus 4, we see that x, as it moves towards 4, and if we plug the number 4 into this expression, we get 16 minus 16 divided by 4 minus 4, which is equal to 0 divided by 0. Now this is known as an indeterminate form. We could resolve this by simply factorizing the numerator, which would be x minus 4 multiplied by x plus 4, and then divide that by x minus 4. The denominator would cancel out with part of the numerator and it would leave x plus 4. So then we'd have the limit as x tends towards 4 of x plus 4. If we plug in the value of x equals 4, we would get that as an answer of 8. Similarly, if we look at the limit x tends towards infinity, 4x squared minus 5x divided by 1 minus 3x squared. So as we can see here, as x tends towards infinity, the numerator tends towards infinity and the denominator tends towards minus infinity. So this again is an indeterminate form. Again, we could resolve this by looking at the limit as x tends towards infinity of, and then if we remove the x squared from the numerator, we get x squared multiplied into 4 minus 5 divided by x, and that would all be divided by x squared multiplied into 1 minus x squared minus 3. So the x squareds would cancel out, which would leave 4 minus 5 divided by x divided by 1 divided by x squared minus 3. So if we now look at what happens when x tends towards infinity, we see that 5 divided by x, so this part here, tend towards 0, and 1 divided by x squared here would also tend towards 0. So we'd be left with the limit as x tends towards infinity of 4x squared minus 5x divided by 1 minus 3x squared would equal, and what we're left with here is minus 4 divided by 3. L'Hopital's rule provides another way of helping to evaluate indeterminate limits of the form 0 divided by 0 or infinity divided by infinity. So if we want to find the limit x tends towards c of some function f of x divided by some function g of x, and where the limit as x tends towards c of f of x is equal to the limit as x tends towards c of g of x, and they both equal 0, or the limits of these two functions are plus or minus infinity. So if this is the case, and the limit as x tends towards c, the derivative of f of x divided by the derivative of g of x exists, then it is true to say that the limit as x tends towards c of f of x divided by g of x is equal to the limit as x tends towards c of the derivative of f of x divided by the derivative of g of x. So now let's look at this in action. Let's take the first example that we looked at, which was find the limit x tends towards 4 of x squared minus 16 divided by x minus 4. Now we found that this limit was indeterminate because it was 0 divided by 0. So let's use L'Hopital's rule to see if we can find this limit. So if f of x is equal to x squared minus 16, the derivative of f of x is equal to 2x, and if g of x is equal to x minus 4, the derivative of g of x is equal to 1. So we know from L'Hopital's rule that the limit as x tends towards c of f of x over g of x is equal to the limit x tends towards c of the derivative of f of x divided by the derivative of g of x. So in the limit, x tends towards 4 of f derivative divided by g derivative is equal to, now derivative of f of x is 2x, derivative of g of x is 1. So if we take x is equal to 4 and we put it into this, we get 8 divided by 1, which is equal to 8. So we've evaluated this limit using L'Hopital's rule. In our second example, we found that the limit as x tends towards infinity of 4x squared minus 5x divided by 1 minus 3x squared was also indeterminate, as it was infinity over minus infinity. So again, let's use L'Hopital's rule to try and evaluate this limit. In this case, f of x is equal to 4x squared minus 5x, and the derivative of f of x is equal to 8x minus 5. G of x equal to 1 minus 3x squared. The derivative of g of x equal to minus 6x. So in the limit, x tends towards infinity of f of x over g of x equals the limit x tends towards infinity of the derivative of f of x divided by the derivative of g of x. So the limit x tends towards infinity of the derivative of f of x, which is 8x minus 5, divided by the derivative of g of x, which is minus 6x. So we can see here, as x tends towards infinity, the numerator, as x gets larger, the numerator tends towards infinity, and the denominator tends to minus infinity. How do we deal with this situation? Well, we take the second derivative. The limit as x tends towards infinity of the second derivative. So the second derivative would be 8x minus 5 would leave 8, minus 6x, the derivative of that would leave minus 6. This would equal minus 4 divided by 3. So let's look at another example and see if we can evaluate the limit as x tends towards 0 of sine x divided by x. So when x is equal to 0, the sine of x is equal to 0 divided by x is equal to 0. So that's an indeterminate limit. So then if we apply L'Hopital's rule to this, we can say that the limit as x tends towards 0 of sine x divided by x is equal to the limit x tends towards 0 of the derivative of sine x, which is cosine x, divided by the derivative of x, which is 1. So at x is equal to 0, cosine of x is equal to 1, divided by 1, which is equal to 1. Let's look at another example. Let's try and find the limit x tends towards infinity, e to the x over x squared. So as we can see, as x tends towards infinity, we have an enormously large numerator and enormously large denominator. So we get indeterminate form of infinity over infinity. So let's apply L'Hopital's rule, see if we can evaluate this limit. So the limit x tends towards infinity of e to the x divided by x squared is equal to the limit x tends towards infinity of the derivative of e to the x, which is e to the x, divided by the derivative of x squared, which is 2x. So again, as x tends towards infinity, we have a case of infinity divided by infinity, which is indeterminate. So we can apply L'Hopital's rule yet again. We can say the limit x tends towards infinity of e to the x, this time divided by 2x, is equal to the limit x tends towards infinity. The derivative of e to the x is e to the x divided by the derivative of 2x is 2. So as we can see now, as x tends towards infinity, this evaluates to infinity. So as you can see, we can apply L'Hopital's rule multiple times to evaluate our limit. Other indeterminate forms that L'Hopital's rule might be able to help with are as follows: 0 times infinity, 1 to the power of infinity, 0 to the power of 0, infinity to the power of 0, and infinity minus infinity. Let's suppose we have a multivariable function where z is equal to f of xy. What do we mean when we want to find its partial derivative? Well, the partial derivative represents the gradient or slope of the tangent line in the direction of the variable being differentiated. This means treating the other variable or variables in the function as constants. So let's say we have a function f of xy which equals x squared y squared. The derivative of f with respect to x, df dx, which has the notation of a curly d, is the derivative of the function with the variable y held constant, and so we only differentiate the x variable. If we go ahead and do this, we can see that the partial derivative of f with respect to x is equal to 2xy squared, which represents the gradient of the tangent in the x direction for any fixed point y. Similarly, df dy is the derivative of the function with the variable x held constant, so we only differentiate the y variable. If we go ahead and do this, we see df dy is equal to 2y x squared, which represents the gradient of the tangent in the y direction for any fixed point x. Now let's take a look at this surface f of xy when we plot it in 3 dimensions. So we have our function z equals x squared y squared, which is represented by the surface shown in red. If I now fix a point on the y-axis, so let y equal 1, you can see we have a parabola formed in the xz plane. Using partial derivatives, we can calculate the gradient of the tangent to the parabola at the fixed point y equals 1 and in the x direction. Similarly, if I now fix a point on the x-axis, so let x equal 1, you can see we have a parabola formed in the yz plane. And using partial derivatives, we can calculate the gradient of the tangent to the parabola at the fixed point of x equals 1 and in the y direction. Let's now use the function f of xy, which equals x squared y squared, and look at what that means in terms of limits if we take the partial derivative of f with respect to x. As we saw, when we held y as a constant, this created a parabola shape, and we could then find the gradient of the tangent to the surface in the x direction. On the graph, I've marked point x and x plus h on the x-axis, and their corresponding points on the z-axis where they meet the curve. In this case, I've held y constant at y equals a. If we now draw a secant between the 2 points, we see that it creates a poor approximation to the gradient of the tangent to the curve at point x. If we now slowly reduce the size of h so that it approaches 0, we see the approximation improves and is perfect at the point x where h is 0. So we can say that in the limit as h approaches 0, f of x plus h comma a minus f of x comma a, which represents this distance here, divided by h, which represents this distance here, represents the partial derivative of the function df by dx when y is held constant at a point a. Let's now calculate the limit as h tends to 0 of the function using these values. So plugging these values into the function x squared y squared, we get the limit as h tends to 0 of x plus h all squared multiplied by a squared minus x squared a squared all divided by h. Expanding this out, we have the limit as h tends to 0 of a squared x squared plus 2xh a squared plus a squared h squared minus x squared a squared all divided by h. This term and this term both get eliminated, and dividing both numerator and denominator by h, we see that h is eliminated from the denominator, and this value of h is eliminated, and this term becomes a squared h, which leaves us with the limit as h tends to 0 of 2x a squared plus a squared h. So the limit as h tends to 0 of 2x a squared plus a squared multiplied by h equals 2x a squared. And this represents the partial derivative of the function f with respect to x at a fixed point y equals a, which is the gradient of the tangent to the surface in the x direction when y is held constant at y equals a. Let's look at how we take derivatives of multivariable functions, that is, functions with more than one variable. To take the derivative of one variable in a multivariable function represents the rate of change of the function as the variable changes while holding all other variables constant. We've looked at how this works with limits, and if you haven't already watched it, please check out this video to further understand the process. Suppose we have a function f of xy. The partial derivative of f with respect to x is given by df by dx, and the partial derivative of f with respect to y is given by df dy. An alternative way of representing this is f subscript x and f subscript y. So now let's take a look at an example of how we take partial derivatives. So let's suppose we have a function f of xy equals x cubed plus y squared, and we want to find the partial derivative of f with respect to x. So that's the rate of change of x when we hold y constant. So to help us understand this, let's set y to be a constant. So let y equal a. So now our function f of xy is equal to x cubed plus a squared, and df by dx, so that's the partial derivative of f with respect to x, is simply differentiating the function with respect to x. And so to evaluate the partial derivative of f with respect to x, so that's df by dx, we take the derivative of x cubed with respect to x, and using the power rule, that equates to 3x squared. And then we take the derivative of the constant a squared with respect to x. And as it's a constant, it evaluates to 0. So we find that our partial derivative of f with respect to x equates to 3x squared. Similarly, we can take the partial derivative of f with respect to y. This means holding the x variable constant. So in this case, we let x equal a. So in this case, our function f of xy becomes a cubed plus y squared, where a is just a constant. And so to find the partial derivative of f with respect to y, so df by dy is equal to the derivative of a cubed with respect to y is equal to 0, and the derivative of y squared with respect to y is equal to 2y. So the partial derivative of f with respect to y is equal to 2y. Now let's look at another example. Let's say we have the function f of xy is equal to x cubed multiplied by y squared. So let's first look at how we find the partial derivative of f with respect to x. So to do this, we're going to hold y constant. So we let y equal a. So f of xy is now x cubed multiplied by a squared. So to find the partial derivative of f with respect to x, we differentiate x cubed a squared, where a is a constant, with respect to x. And using the power rule to do this, we find that its derivative is 3x squared a squared. So now if we replace a with y, we see that the partial derivative of f with respect to x is equal to 3x squared y squared. And to find the partial derivative of f with respect to y, we can hold x constant. So let's let x equal a. So f of xy equals a cubed y squared. And so to find the partial derivative of f with respect to y, we need to find the derivative of a cubed y squared with respect to y, where a is a constant. So using the power rule, the derivative of a cubed y squared with respect to y equals 2a cubed y. And now, if we substitute x in for a, we find that the partial derivative of f with respect to y is equal to 2x cubed y. There is an alternative way of looking at this problem. We can look at f of xy as the product of two functions, so u of xy and v of xy, where u of xy is equal to x cubed and v of xy is equal to y squared. We can then use the product rule to find the partial derivative of f with respect to x and the partial derivative of f with respect to y. Using the product rule, the partial derivative of f with respect to x is equal to the partial derivative of u with respect to x multiplied by v plus the partial derivative of v with respect to x multiplied by u. And so the partial derivative of u with respect to x is the derivative of x cubed with respect to x, which is 3x squared, and that's multiplied by v, and v is y squared, plus the partial derivative of v with respect to x, where v is equal to y squared. Its derivative with respect to x is 0, as y is seen as a constant, and this is multiplied by u, where u is equal to x cubed. So the partial derivative of f with respect to x is equal to 3x squared y squared. And using the product rule to evaluate the partial derivative of f with respect to y, we have the partial derivative of u with respect to y multiplied by v plus the partial derivative of v with respect to y multiplied by u. The partial derivative of u with respect to y, where u is equal to x cubed, and in this case treated as a constant, is equal to 0. We multiply this by v, where v is equal to y squared, so we have 0 multiplied by y squared, plus the partial derivative of v with respect to y, where v is equal to y squared, we can find using the power rule. So its partial derivative is 2y. We multiply this by u, where u is equal to x cubed, and we see that the partial derivative of f with respect to y is equal to 2y x cubed. Now let's look at the function f of xy, which equals y squared multiplied by sine x, and find the partial derivative of f with respect to x and the partial derivative of f with respect to y. Beginning with the partial derivative of f with respect to x, we hold the y variable constant and take the derivative of the x variable. So when we do this, we see that the derivative of sine x with respect to x is cosine of x, and that's multiplied by y squared, as it was held constant. And so the partial derivative of f with respect to x is equal to y squared cos x. And for the partial derivative of f with respect to y, we hold the x variable constant and we differentiate the y variable with respect to y. So the x variable, sine of x, is held constant, and the derivative of y squared with respect to y is 2y. So we have the partial derivative of f with respect to y equals 2y multiplied by sine x.